If you'd recall, yesterday we calculated a line integral of this vector field, 6xi plus yj, over the curve C1, which was the line from 2, 0 to 0, 4. So that was a lot of fun because we got to parameterize the line from 2, 0 to 1, 4. And then we got to calculate the definite integral by taking the dot product that gave us an integral from t equals 0 to t equals 2 along this path. Evaluating this vector field at all the points along this path, calculating the dot product with this with the direction vectors along this curve, and then adding all those things up. So that was cool. Calculating a line integral, we had to parameterize a curve, we had to do the dot product, we had to write the vector field in terms that the integral could understand, and we come up with -4. So that seemed kind of a little bit anticlimactic, because we're like, oh, and after all this work, it's a -4. But we do have an intuition with this. We know that when the curve is generally going against the vector field, when our bird is flying into the wind, our line integral will give us a negative value. So the orientation of the curve is generally against the vector field. So the curve is trying to go broadly from right to left, and the vector field is broadly trying to go from left to right. And that's mostly being, it's also going up because we're in the first quadrant, and this yj is making the vector field go up. But the 6x is pushing the vector field from left to right, except at the y-axis where it's going directly up. So generally, the orientation of the curve is against the vector field. All right. So today, we're going to parameterize the curve C2 and then calculate this vector field, calculate this line integral again. Any questions before we begin? Great. Yesterday, I also mentioned that there was something suspicious about setting up this one vector field and these two different curves that have the same starting and ending point. Does anybody want to speculate what the line integral over C2 of f dot dr is going to be? It's okay if you don't want to type it out loud. We don't have our mics on, so we don't want to type things out loud. So let's get to the business of calculating this line integral. First, we need to parameterize the curve C2. So we're going to start by parameterizing the curve C2. We want to find the integral over C2 of f dot dr. First, we're going to parameterize the curve C2. I think that's only the third time I've said that, so. The advantage that we have here is that C2 can be described with a function. We see that C2, the curve C2 is actually the function y equals 4 minus x squared. So we have a bit of an advantage. The curve can be described where y is a function of x. That means that's where we should start trying to describe what's going on. So we should say, since y is just 4 minus x squared, let's make x the parameter and write y in terms of x. So x is equal to t and y is equal to 4 minus t. However, we have the same problem. If we run t from, say, what makes sense, x goes from 0 to 2. So if we run t from 0 to 2, our curve goes backwards. So we notice that the x values that are in play are between 0 and 2. But if we run t from 0 to 2, then our curve will go the wrong direction. So we notice since x is between 0 and 2, but if we use if we run 0 to t from 0 to 2, then our curve goes in the wrong direction. Because that would be here's t equals 0 and here's t equals 2. That's going the wrong direction. So we're going to correct this the same way we did yesterday. We're going to reverse the x. I need a longer arrow. We're going to reverse the x. I'm going to pull the Uno reverse card. I don't know if Uno is still a thing, but it used to be. And I'm going to say x is 2 minus t, and now x is going in the opposite direction. And then we could do the same thing for, we're just going to write y, oops, t squared. We're going to write y as 2 minus x squared. In this case, x is 2 minus t. So now we have an expression for x and an expression for y. We have a range of t's to plug in, maybe a domain of t's to plug in. We'll just integrate from t equals 0 to t equals 2. And this will parameterize the curve so that it goes in the correct direction. So let's review that because this is the thing that we did yesterday. This is the thing that we did yesterday, and this is the confusing thing. So I started off with x equals t and y equals 4 minus t squared. The reason for that is that y is already a function of x. So it's easy to get x and y to work together. So that's why I started with this parameterization. But if I put at t equals 0, if t equals 0, then x is 0 and y is 4. So what I mean by the curve goes the wrong way, when t equals 0, we get x equals 0 and y is equal to 4. That's where we want to end. And when t is equal to 2, we get x equals 2 and y is equal to 0. So this is the wrong direction. T goes from 0 to 2. So one way we can deal with this, we want x and t to go in opposite directions. I want to have x count down from 2 to 0 instead of count up from 0 to 2. So while t goes up from 0 to 2, I want x to count down from 2 to 0. And that's what this 2 minus t will do for us. So writing x as 2 minus t, this will, x will count down from 2 to 0, while t counts up from 0 to 2. Now, x will count down from 2 to 0, while t counts up from 0 to 2. And we can see that by plugging in these values. If t is equal to 0, then x is equal to 2 minus 0, or 2, and y is equal to 2 minus did I go backwards? Needed. So when t is equal to 0, this is 2 squared is 4. 2 minus 4 is, what did I do wrong? Oh, 4, thank you. Yikes. I mean, well done. You found my carefully planned mistake. This should be a 4. This is a 4. This should be a 4. Phew. Thank you. Nice save. So now when t is equal to 0, 2 minus 0 is 2, squared is 4, 4 minus 4, y is equal to 0. Whew, save me on that one. I would have never seen that because I had just done that. So now when t is equal to 2, so this is our starting point at 2, 0. That's what we want, to start at 2, 0. Now when t is equal to 2, x is equal to 0, and y will be equal to 2 minus 2 is 0 squared, 4 minus 0 is 4. So now our start point is at 2, 0, and our end point is at 0, 4. Whereas before, our starting point was 0, 4, and our ending point was 2, 0. That was backwards. Any questions? This isn't the only way we could have done this, but this is a handy skill to acquire. So that's why I'm doing things this way. Also, I mean, fun. So remember that when we're doing a line integral, the curve has to have some direction, and we want to make sure that the direction matches, because it's a complete disaster if the direction doesn't match. Or we just multiply by -1 if we realize that at the end to go the other direction. It's nice that our algebraic instincts are still going to work when they kick in. So now that we have a parameterization for C2, we can start building the line integral. We know what C2 is going to be. So C2 now has a parameterization. So the parameterization of C2, oops, it's not going to be good spacing there. So C2 is given by this vector, r of t. The x is 2 minus t, I, and the y is, I'm going to clean this up a little bit. So 2 minus t squared, we have 4 minus 4t plus t squared. So 4 minus 4 cancels out, so we'll have 4t minus t squared. That cool? Just hit this with the algebra stick. See, now I'm all paranoid. I'm checking my algebra, double careful. So I'm going to write y as 4t minus t squared j for t between 0 and 2. So we're going to need this in the line integral to plug these two values in for the x and the y. What we've said is that x is equal to 2 minus t, and y is equal to 4t minus t squared. That's if we start at t at 0 and end t at 2. We also need the dr parts. So the dr is going to be the r prime of t. So the derivative of 2 minus t with respect to t is going to be a -1 times I. And the derivative of 4t minus t squared is going to be 4 minus 2t j. And then all this dt. Just take the derivative of each of the terms. And now we're ready to start putting things together into the line integral. So the integral over C2 of f dot dr, it's going to be integral over the t values. So t is running from 0 to 2. I'm going to need the vector field f evaluate it at the parameterization, so we're x with x and y, so 6x, so it's 6 times x, 2 minus t, I, plus y times j. That's f of r dot dr, which is all this up here, minus I plus 4 minus 2t times j dt. So this part here is f at r prime, sorry, f at r, and this is all dr, which is r prime dt. So now we have taken the vector field and written down what the vector field looks like at every point on the curve C2. I've written down dr, which is the direction that the curve is going at every point along the curve from t equals 0 to 2. And we're going to calculate the dot product of the vector field and the direction the curve is going. And then we'll evaluate, then we'll integrate and evaluate from 0 to 2. So let's do that part. So I need the dot product. So I multiply the i's. So I'm going to clean this up a little bit. Maybe. Yeah, let's do that. So this is going to be 12 minus t. This one doesn't need any cleanup. This is still 4t minus t squared. But when I multiply 12 minus t times -1, so 12 minus t times -1 is going to be t minus 12 plus, because dot product, 4t minus t squared times 4 minus 2t. And all that, we haven't integrated anything. We're just doing the dot, doing a dot product. So this is all still dt. Any questions? Now we just got an integral dt, so we got to get all this cleaned up. So let's clean that up. What do we got here? We got 16t minus 8t squared minus t squared minus 4t squared plus 2t cubed, and then we still have plus t minus 12. So we're going to be integrating, I can't read it this way. We're going to be integrating from 0 to 2. Let's see. 2t cubed. It's 12 minus 6t, thank you. And so this is going to be 6t minus 12. So this will be 6t minus 12. Thank you. That's a good catch. My next carefully planned mistake. You caught it. That's 1,000,000 points for you and 0 for everybody else. I'm just kidding. It's 0 points for you and -1,000,000 for everybody else. So I got 2t cubed minus 12t squared plus 22t minus 12 dt. So this first stage was just doing the dot product. This second stage is just doing some algebra. Hopefully I did the algebra well. Now we can integrate this. Any questions? Comments? Let's integrate this. If you hear buttons being pressed, I assure you I'm not doing this on a calculating machine. I'm totally just doing this by hand or in my head, not even doing it by hand. So I totally didn't use my calculator to do this definite integral. Whoops. The reason that I want to skip this step is because, first of all, that's two like little algebraic mistakes. So apparently I'm going to add like 1 to here and I'll end up with 10. So could be a disaster. But this would be easy to calculate. So we would just add 1 to the exponent, divide by the new exponent, plug in the endpoints. We just add 1 to the exponents. So it's going to be t to the 4th over 4. So 2/4 is a half. See, this is where it's dangerous. T to the 3rd. And then 12 divided by 3 is 4. And then t squared divided by 2 minus 12t evaluated from 0 to 2. Really, that would just mean we plug in 2, but we come up with -4. So this is the interesting part. We integrated this vector field over 2 different paths and came up with the same value. We integrated the same vector field over 2 different paths and came up with the same value. We integrated f over 2 different paths from 2, 0 to 0, 4 and got the same value. That is surprising because we should expect something different to happen. If we go from point A to point B, if we have our bird fly from 2, 0 to 0, 4 along this line, and then another bird fly from 2, 0 to 0, 4 along this parabola, we should expect them, we might expect them to do different amounts of work. But they didn't do different amounts of work. They did the same amount of work. Moreover, it doesn't matter which path we take from 2, 0 to 0, 4 for this particular vector field. That's the interesting thing that's going on in this problem. This vector field doesn't care about what path you take because this vector field is a gradient field. The vector field is path independent because the vector field is a gradient field. So this vector field is what we'll call path independent. It doesn't matter what path we take from one point to the next. We'll always get the same value. The reason that we know that this particular vector field is path independent is because this vector field is a gradient field. That is, it is the gradient of some function f. Gradient fields are path independent. It's cool in calculus when we can say big things like that. Gradient fields are path independent. the function f will be called the potential function of the vector field. Because the gradient of f is equal to that vector field f. Any questions? All right, let's pause the video here and talk about the next steps. This was the cool part, by the way, discovering that f was a vector field and therefore is path independent. And even though it seems like it should be very different how we go from one point to the next, if we're doing a line integral of a gradient field, the path don't matter. We just, whichever one is easiest to compute, use that one. All right, let's pause the video here and talk about next steps.